Hello everyone. This is Information Theory and Coding, the Module 2 Source Coding. This is the session 2. The course outcome of this is what the study the various source encoding algorithms. So we are going to look into this particular session is the Shannon's first theorem, that is also called as a noiseless coding theorem, and the Shannon's encoding algorithm, and some questions on this particular topic. The Shannon's first theorem, or what we call it as a noiseless coding theorem. What is going to be suggest? So what is the minimum length is required to each and every particular codes? So with the help of what the probabilities of occurrence of each and every symbol. So we are going to be calculate the length. So by looking into that aspect, so Li is equal to log R 1 divided by log of 1 by pi with a base R. So certainly when we are going to be calculate all these values or the length of the particular code, we are going to be calculate with the base 2, that is in terms of what the bits. So by changing r equal to 2, we'll get length in terms of bits. So if I require the ternary codes, then r must be 3, then we are going to be call it as a trinits. If it is r equal to 4, we are going to be call it as a quaternary units. So like that we are able to what the calculate the each and every length of a given symbol with a respective probability. But by calculating the lengths, so obviously we are going to be get what the fraction values of Li, and it is very difficult to write a binary values in terms of the fractions. So for that reason, Shannon has suggested whatever the codes you are going to be write, those things should be in what the integer digits. So whatever the values you are going to be write for the codes, it should be in the form of what the integers. So when you are going to be write the above by using the above equation, that larger the value of the symbol probability, smaller will be the value of Li. That already we have seen what when the information is always inversely proportional to the occurrence of its probability. When the probability is more and more, then information is less and less. So with the help of the same equation, we are going to be write what the length of its bits. So where if Li happens to be a fraction as calculated from the equation 1, so then it is rounded off to the next integer value as given by the equation log of 1 by pi is always less than or equal to Li and is always less than or equal to 1 plus of log of 1 divided by pi. This is going to give us that the lower bound on the average length. So that Li is must be what the rounded off to the integer values. So if you take it's a binary form, then certainly we have to divide the each and every term in the equation 2 as log r with a base 2, and by changing the numerator with the base as a 2, that is a log of 1 by pi with a base 2 divided by log r with a base 2, that is less than or equal to Li is less than or equal to 1 plus of log of 1 by pi with a base 2 and divided by log of r with a base 2. Again, multiplying this throughout by pi and taking the summation, that will for all I varying from 1 to q, we get what is that 1 divided by log r is a constant that I have taken outside the summation sign, and summation is going to be take from I equal to 1 to q. Pi log of 1 by pi is always less than or equal to summation of I equal to 1 to q pi into Li, and less than or equal to summation of I equal to 1 to q pi plus of 1 divided by log of r, that is also constant we have taken outside of the summation sign, and then we can write a summation of I equal to 1 to q pi log of 1 by pi. So we know that, so what we know that is the entropy of the given function is what summation of I equal to 1 to q pi log of 1 divided by pi, and average length is summation of I equal to 1 to q pi into Li, and the probability, sum of the probabilities must be equal to 1. This we know the already in the previous sessions we have studied what how to calculate the entropy of a function, how to calculate the average length, and the sum of the probabilities of all the events must be equal to 1. So substituting all these in the above equation, so we get what is that h of s divided by log r with the base 2 is less than or equal to capital L, that is the average length, and less than or equal to 1 plus of h of s divided by log r with the base 2. And we know that how to write the entropy for the different symbols, that is like r if you are considering as a 3, as a 4 for the ternary units, quaternary units, then h of s divided by log r with a base 2, and that is nothing but what h of s with a base as a r like a thing. And substituting this in above equation, we get it as what the hr of s is less than or equal to L and is less than or equal to 1 plus of hr of s. What it is going to be saying? So always whatever the length you have calculated, that is the average length, is always greater than or equal to what the entropy of the given function. From the equation 7, it is clear that the average word length is always greater than or equal to the entropy of the given source. So Shannon suggested that the equation 5 still holds good for the nth extension of the source. So as we get what the better efficiency. So whenever you are going for the any extension version of the source, we are getting what the betterment of the, so h of s may be what the closer to the L, or L may be what the closer to the h of s, and we may enhance what the efficiency of the source. So like that, the h of s to the power of n divided by log r with the base 2 is always less than or equal to ln, is less than or equal to 1 plus of h of s to the power of n divided by log r with the base 2, where ln is the average length of the code words of the nth extended source symbols. And as we know that the entropy of the nth extended source is h of s to the power of n is equal to n into h of s. Substituting in above equation, we get it as what, as already we have seen the nth extension of a source, h of s to the power of n can be written as n into h of s. So n into h of s divided by log r base 2 is less than or equal to ln, and is less than or equal to 1 plus of n into h of s divided by log r with the base 2. So dividing this throughout by n, we get hr of s is always less than or equal to ln by n is less than or equal to 1 by n plus of hr of s. By considering the limit n taking to the infinity from the first inequality in the equation 10, we get it as what the limit n tends to infinity ln divided by n is equal to hr of s. So when L is the average length of the code words for the basic source S, then for all values of the extended n, it is a true for ln divided by L is always less than or equal to L. Yeah. Code efficiency and redundancy can be calculated with the help of the equation, that is eta c equal to h of s divided by L, and eta c for the other codes or the R array codes, we can able to write it as hr of s divided by L, and eta c is always less than or equal to the 100%. So obviously because L is always greater than or equal to EH, therefore so it never be crosses for the 100%. So therefore the efficiency of the given function or the given source we can able to calculate with what the code is always less than or equal to 100%, and the code redundancy is denoted by r eta c equal to 1 minus of eta c, where eta c and r eta c are usually expressed in terms of the percentage. Next, Shannon's encoding algorithm. So how to make use if you are having what the set of symbols are assigned and a set of probabilities are given for the respective symbols. So how to calculate the respective codes for the S1, S2 to SQ. So by using Shannon's encoding algorithm, these are the following steps we have to consider while constructing the codes by using Shannon's encoding algorithm. First step is list the source symbols in the order of non-increasing probabilities. So in whichever the order the source symbols are going to be emit with the respective probabilities, first thing we have to arrange in the non-increasing probabilities, means it is in the decreasing order. So given s equal to s1 to sq, and where p equal to p1 to pq, and there must be what, p1 must be greater than or equal to p2 must be greater than or equal to p3, and so on, it must be greater than or equal to pq. So in that way we have to arrange the given probabilities. Next step, that is a step 2, is compute the sequences of alpha. Alpha 1 is equal to 0 and alpha 2 equal to p1, that is nothing but p1 plus of alpha 1. So it is nothing but what, just what the cumulative add up of the given probabilities, and at the end of that alphas, that must be 1, that is alpha q plus 1 is equal to pq plus of pq minus 1, and so on, p2 plus of p1 is equal to pq plus of alpha q. So you have to calculate, and that alpha q plus 1 must be equal to 1. That is a cumulative addition of the probabilities. Step 3. Determine the smallest integer value of Li using the inequality. That is 2 to the power of Li must be greater than or equal to 1 divided by Pi. So whenever you are considering the any value of the Li, so if it is more and more, then obviously it is going to be satisfy the this inequality. But we have to what, find out the smallest integer value of Li that must satisfy this inequality. That is a step 3. Step 4 is what, expand the decimal numbers of alpha I in binary from up to Li places, neglecting expansion beyond the Li places. And last step is what, remove the binary point to get the desired code. So let us consider one example. Say example, apply Shannon's encoding algorithm to the following set of messages and obtain the code efficiency and redundancy. So there are 5 messages, M1, M2, M3, M4 and M5. Respective probabilities are 1 by 8, 1 by 16, 3 by 16, 1 by 4 and 3 by 8. So solution for this is what, first step we have to follow, that we have to rearrange all these messages probabilities in terms of what, the non-increasing probabilities. So that is by making its a denominator same. So M5 will get the highest value, that is a 6 by 16. M4 will be the next highest value, that is a 4 by 16. M3 is a 3 by 16. M2 is 2 by 16 and M1 is 2 by 16 and M2 is 1 by 16. So now we have to assign the probabilities like a P1, P2, P3, P4 and P5. Now by looking into that aspect, P1 is greater or equal to P2, P2 is greater or equal to P3, P3 is greater or equal to P4, P4 is greater or equal to P5. Now, step 2 is what, the following sequence you have to compute the alphas. So first thing we have to consider alpha 1 equal to 0. Next, alpha 2 equal to 6 by 16, that is a P1. That I have written in terms of what, the decimal number, that is a fraction value, that is a 0.375. Then alpha 3 is equal to 6 by 16 plus of 4 by 16. You will get 10 by 16. The value is 0.625. Alpha 4 equal to 10 divided by 16 plus of 3 by 16. You will get 13 by 16. And the fraction value is 0.8125. Alpha 5 is equal to 13 by 16 plus 2 by 16. We will get a 15 by 16 is equal to 0.9375. And lastly, that is alpha q plus 1, because we are having a 5 number of symbols. Q is 5, and as already what we have discussed in the procedure, alpha q plus 1 must be equal to 1. That is alpha 6 equal to 15 by 16 plus of 1 by 16 equal to 1. Step 3, we have to find out the smallest integer value of Li is going to be found using 2 to the power of Li must be greater than or equal to 1 divided by Pi for all I equal to 1 to 5. So Li is greater than or equal to log of 2 1 divided by Pi can be written. Okay, if I take I equal to 1, so that means L1 is greater than or equal to log of 1 divided by P1. So if I write log 2, sorry, log of 1 divided by 0.375, whatever the P1 I have got, so with the base 2, so in order to satisfy this particular inequality, I have to choose as a L1 as 2. And then L2 can be written with a log of 1 divided by P2 and log 2 of 1 by 0.25. It can be written with what? Log of 4 with the base 2, and therefore the smallest value of L2 is 2. Then L3 in the similar way we can able to calculate, and in order to satisfy this I have to choose L3 as 3 and L4 as chosen as 3 and L5 as chosen as 4. Though I am not taking it as a L3, L4, L5 as 3, 3 and 4, even if you take as a higher values, still it is going to be satisfy this inequality. But what the procedure is going to be said, that you have to choose the smallest integer value to satisfy these inequalities. So L1 is 2, L2 is 2, L3 is 3, L4 is 3 and L5 is 4. So now we have to expand the given alphas in terms of what, the binary values, or we have to convert it up to Li places. So alpha 1 is equal to 0, any of 0 will be written in binary also 0, So we can write it in how many number of bits we require. We can write as a zeros. Then alpha 2 is 0.375. We can convert it back in terms of what the binary. We'll get what the 0.011. Then alpha 3 equal to 0.625. That can be converted in terms of binary. We'll get as a 0.101. Then alpha 4 equal to 0.8125. We'll get a 0.1101 in terms of binary. Then alpha pi equal to 0.9375, and we can convert it back in terms of binary is 0.1111. That is a 4 ones. Then the last step, that is a step 5, we have to ignore or neglect that binary point, and we have to rewrite the codes up to what the li places for S1, S2, S3, S4 and S5. Now consider alpha 1 is equal to 0, whatever the we have taken, and where L1 equal to 2, therefore the code for S1 is 0, 0. Then alpha 2 equal to 0.011 and L2 is 2, and by neglecting the binary point and considering L2 as 2, we can write it as a code for S2 is 0, 1. Then alpha 3 equal to 0.101 and L3 equal to 3, therefore the code for S3 is 101. Then alpha 4 equal to 0.1101 and L4 is equal to 3, therefore the code for S4 is 110. And alpha 5 equal to 0.1111 in terms of binary and L5 equal to 4, therefore the code for S5 is all ones, that is a 4 ones. So this is what the code we have designed or the constructed by using the Shannon's encoding algorithm. Then by writing that all the codes in terms of a table, so there the source symbols we have written as a M5, M4, M3, M1 and M2, and the respective probabilities are 3 by 8, 1 by 4, 3 by 16, 1 by 8 and 1 by 16. And the respective codes are the what we have constructed as a 0, 0, 0, 1, 1, 0, 1, double 1, 0 and all ones, that is a 4 ones. So LIs we have written as a 2, 2, 3, 3 and 4. So respective lengths for M5, M4, M3, M1 and M2 0. Then we have to calculate the average length for the constructed code. So by using the equation L equal to summation of I equal to 1 to Q Pi into Li, where Q is equal to 5. So just write the respective probability and the respective lengths, product of that, and then you add it and you will get it as L equal to 0.4375 minutes per message symbol. Then entropy of this particular code can be, or the given probabilities can be calculated as h of s equal to summation of I equal to 1 to q pi into log of 1 by pi, where q is equal to 5. By using this equation, if you operate if you calculate it, you will get it as h of s equal to 2.1085 bits per message symbol. Therefore, the code efficiency is calculated by using eta c equal to h of s divided by L, and that is equal to 2.1085 divided by 2.4375, and it gives you 0.865. In terms of percentage, we can write it as a eta c equal to 86.5%. And code redundancy is calculated as R eta c equal to 1 minus of eta c, that is equal to 1 minus of 0.865, and it gives you 0.135, that is nothing but 13.5% is the redundancy of this particular code. And these are the some questions enlisted of this session, that is, state and prove the Shannon's first theorem, list the steps involved in Shannon's encoding algorithm, and lastly construct binary code for the following source using Shannon's binary encoding procedures by given S1, S2, S3, S4 and S5 with the 0.3, 0.2, 0.2, 0.15 and 0.15 probabilities of S1 to S5. And this is the conclusion. This session concludes Shannon's noiseless encoding theorem. Thank you.